tomorrow, because today will be the end of the drop ad, and I'll send you guys who else is on the list and so on, and then you can then start thinking about projects and so on. I'll also probably set up the mailing list and access to wiki, all those things I'll do starting tomorrow. Any questions before we start? Okay, so my understanding of what we're going to do today is we're going to mostly discuss planning. All of you have read the chapter on planning, okay? Just before I get there, this was one slide that I was planning to talk about last time, and I was just going to do that. It's sort of useful to keep in mind. Maybe you can add to these trends in AI. Maybe either already you know some of the trends, or you may be able to add by the end of the semester. Essentially, what I watch, in the field as a whole. One of which is top-down versus bottom-up. The right-hand side presumably is where the pendulum is swinging towards. In fact, I used to call this pendulum swings in AI. I don't think any one is the right one. You need both. But research being a generally human process, people will all be in some bandwagon for a while and then going to a different bandwagon after a while. And it will be useful to sort of know what are the choices in the bandwagon, so in case you want to pick. So top-down versus bottom-up, of course, is the idea that you would start, in the top-down case, you essentially start assuming that you would, develop knowledge representation, you will develop reasoning with the knowledge representation, and then slowly at some point of time it peters out into the perception. Okay, that's sort of a top-down approach. Bottom-up approach, and actually I think a large amount of, what's called a logical AI can be characterized that way. And the bottom-up approach is actually more the opposite direction. Let's just start from the perception and see what we can do, and then keep adding higher level reasoning and higher level representations, etc. slowly. Okay. Now, currently, many a time what happens is currently there are people doing top-down, there are people doing bottom-up. There is a hole in the middle. There is not too many people actually combining perception and higher level reasoning. And so that's actually some of the more interesting work that's going on within AI. A related idea, actually slightly different, although it's actually shifted this way maybe, is in terms of the representation languages, are you doing reasoning at the ground level, or are you doing at the lifted level? Are you doing reasoning in terms of the instances of the world, or in terms of large properties that will hold over classes of instances? And what's interesting actually about this is a quote attributed to Fernando Pereira, who actually is a pretty well-known natural language processing guy who's currently been sucked up by Google, and he's doing their statistical natural language processing. He started in logical approaches, Montague grammars, etc., to natural language processing, and but he finds himself now doing mostly starting from bag of words model and trying to do better. Okay, so he's sort of become much more bottom-up than he probably wished. And if you're born bottom-up, you don't know that there is another world. But this guy was born top-down and decided to be in the bottom-up world because that's what seems to be working quite well right now. And so he said something to the effect that the longer I live, the farther down the Chomsky hierarchy I seem to be falling. Okay, so he's going down and down in terms of the more ground representations. In fact, one of the interesting things, if we'll actually look at this, some of these actually come up. This one, for example, comes up in the planning discussion. Okay, originally automated planning was done very much in the lifted and quantified representations. Originally, automated planning was seen as a direct theorem proving in situation calculus. You throw planning as a theorem proving problem in situation calculus and you're done. Okay, that just was not scaling up. Okay, and so then much of the work that actually is going on right now is write all the actions as ground actions with everything is directly propositional representations. So we'll look at representations in, I think, some toy worlds where we act as if there are objects, but really what the reasoner is seeing are, here is an action with a bunch of propositions as its preconditions and a bunch of effects, bunch of propositions as its effects. So it doesn't really have a relational view of what it's doing. Okay, so that's something that has happened a lot in the recent years, and there is always there is now more and more, at least at the research level, there are papers, for example, in all the top level conferences, which are trying to get back to lifted representations, because there are some great advantages for being able to deal with quantified lifted representations as against ground representations. So that's another thing. That's one more of the trends that I see across. This actually happens in planning, it happens in machine learning, it happens in pretty much anything you pick. Okay, pure inference and pure learning versus interleaved inference and learning. People tended to segregate themselves into, we are learning people, and we don't quite care. Once we learn knowledge, we'll learn some more knowledge, but we'll never really use the knowledge we learned to learn more knowledge. Okay, to be able to use the knowledge you learn to learn more, you actually need to use it in some sort of an execution. But if you see much of machine learning currently, the most successful parts of the machine learning just look at masses of data and look for patterns in it, and then those patterns are used by somebody else, not by the reasoner which actually found those patterns. Okay, and so essentially, the same thing can be said for the reasoning folks, constraint satisfaction and planning folks assume we are only interested in pure inference problem. You are going to give me the complete specification of the problem, okay, and I'll just what I'm doing is inference, not learning. Okay, but that's also a crazy assumption, because who is always giving you the complete and correct description of any word? Okay, so again, I think the state of the art is largely people separating themselves into, we are the learning folks, we are the planning folks, we are the CSP folks. But there's more and more interesting work actually is starting to get done, but has to also get done, which involves interleaving inference and learning. Okay, and so you have to deal with partially specified models, for example, in planning, and then still try to come up with a plan, and then execute it and fail and learn something, and then that improves your model. And doing that is is more of a trend currently. This is sort of related to this, which is, do you just assume that somebody will sit down and write the model for you? Okay, or you are assuming that you can learn the model from scratch? What really has to happen is somewhere in between, because in the worlds where humans have some sort of an expertise, there is no real reason for you to start from scratch and learn everything. But on the other hand, there are also worlds where humans don't quite know how to write the knowledge that they know. So for example, how do you swim? I'm talking about swimming because I'm trying to belatedly learn to not sink, in my old age. And it's like, it turns out that there are no videos that I can just watch and figure out how to swim, right? There is no book that I can read to figure out how to swim, because people who seem to swim don't quite know how to explain how to swim well. Okay, so, and the same thing, and so in fact, in those cases is where, if you notice, that some of the best, again, I'll assume in these discussions that since this is a graduate class, that some of you already are sort of aware of what's going on in AI. But then, if not, that's okay. You heard here for the first time. It may be repetition, but you may heard also for the first time. But if you're keeping track of what are like some of the star applications of, let's say, machine learning technology, one of the ones that people talk a lot about is this helicopter control, through reinforcement learning. Now, that's like a great machine learning technique. I mean, that's like a thing that's useful for machine learning, because they don't need to start with knowledge and learn more knowledge on top of it, which seems to be the way human learning works. I mean, we don't come with tabula rasa, we don't come with a blank slate, and then try to figure out what is being said in the class. You're learning whatever, whatever you're learning, and in the context of what you already know. Okay, whereas something like helicopter control, for example, there is not that much that people can write down declaratively as to what is supposed to be done. And furthermore, in fact, the specific example I have in mind is some work by Andrew Ng, who got a lot of publicity for this work, and he essentially just has a simulator over which he sees a gazillion billion helicopter simulations, the correct flying simulations, and then learns from that. Okay. One interesting thing is, if you have a human in the loop and somebody is trying to teach you something, they are not going to give you gazillion billion examples. They don't even give you more than one example oftentimes. Okay, we tend to seem to learn from few examples and massive amounts of knowledge. Whereas most of the successful machine learning that we seem to know how to do right now starts with very little background knowledge and massive amounts of data. Now, there are great applications for both of them. And the one that obviously is working, you'll find the applications for that right now. And so the one, the only machine learning right now that anybody hears about is data mining and, basically learning from massive corpora of the language. Okay. So somewhere in between, where you have some knowledge to begin with and you are learning on top of that, that is again an important consideration, that there isn't that much work on that, and it's worth actually thinking about. And then finally, one other thing that I threw in there is human aware versus standalone. There is this curious ambivalence in AI as to whether humans are good or bad. Okay, in the sense, do we want to replace them or do we want to actually work with them? And if you want to replace them, don't be surprised that nobody wants to give you jobs for developing technology that will replace humans eventually. More often than not, you have to deal with humans in the loop. Okay, and the question, of course, is when the humans are in the loop, certain problems become important, even if in fact they have no real reason as to why an intelligent agent should have those properties. So, for example, a classic case is humans have emotions. You can argue until cows come home as to whether or not emotion has any connection to intelligence. Okay, but this much is for sure. If you are writing a program and your friend is writing a program, both of which are supposed to help humans, and your program basically, whenever the human actually screws up, your program says, "Yay, that's great, you screwed up," and your friend your friend's program tries to show some sort of pseudo sympathy for the failure. Okay, clearly you know which one is going to be adopted by humans. Okay, so whether or not emotions are important for intelligent agency, emotions are very much important to deal with these carbon life forms that we are stuck with, who seem to kind of have emotions built in, and you need to sort of deal with them, and so you need to actually understand some of those things. So for example, in a project that we are involved in, which is actually, in fact, this is a sort of an application where you might have humans and robots being working together, let's say, in an urban search and rescue scenario. Okay, so there's the building which has been sort of damaged, and then some robot goes in, and then the human is in telecontact and trying to, but not remote controlling the robot because they don't have complete map. Okay, so robot has the autonomy, but the human and robot are working together to solve some problem. Okay, in those kinds of situations, one interesting thing that one of our co-workers was focusing on in this project was the effect of affect. I may not have said it right. It's effect of affect. Okay, affect essentially is changing the tone of your voice. So you say, "Don't go there," versus "Don't go there." Okay, "Don't go there" in that other way basically means, "My God, you're not listening to me. You have to stop right now." And we actually, I mean, I have a 13-year-old son, and I know this works wonders. When I say, it may be a good time to start sleeping, or it may be a good time to wake up to go to school, in a reasoned way for about 8-10 minutes, nothing happens. Then you kind of increase your affect, not affection necessarily for the kid, but affect. And then somehow he seems to figure out that, yeah, the world is going to end if I don't get up. Now, the point is, if a robot is working, instead of a kid, I have a robot, right? And then if I change my voice and the robot just does simple speech recognition and says, yeah, it's the same thing, who cares about the fact that he has a slightly funnier voice, right? It's not going to help. You actually need to understand that, that squeakiness of the voice actually conveys extra information for these carbon life forms. And since you're dealing with the carbon life forms, they better also convey something for you. Okay, there's a whole bunch of additional other things that actually happen when humans are in the loop. For example, it's not enough to just do something for the human in the loop. If you are trying to help humans, you can't just imagine you ever had I know many of you no longer deal with travel agents, but you just do your own work. We are all our own travel agents, our own search engines, our own everything. We no longer need secretaries and travel agents. But in those days when you had a travel agent, suppose you called them and said, I need a ticket to go from here to here, and they said, here's the ticket. That won't be good, because you'd feel, how dare you think you know exactly what I want. You're supposed to give me some options, And again, going back to my son when he was younger, I'd say, what do you want for breakfast? First question he asks is, what are my options? Okay, so let me tell me what sorts of things you are offering me, and I'll pick one. And it's not so much that, the important thing is you need to provide the human in the loop some measure of control, first of all. And furthermore, the reason options might be important is humans may not be able to completely articulate what their preferences are. And if you don't, and it's very easy to write, for example, optimization programs that, given a preference, a particular objective, can come up with a optimal plan or optimal entity for that. Okay, but what if you are optimizing with respect to the wrong metric, because the humans in the loop don't know how to say what they're really interested in. Okay, so then you will have to start thinking about generating diverse plans. For example, if you're into planning, you have to generate diverse plans and show them. Okay, and my favorite example for this, pardon me for those of you who have heard this before, if you, for example, search on a search engine, let's say for my name, okay, I do come first, but then they'll throw in a couple of other loser compom parties in the first top 10 results. And I never understood why it makes sense to even look at other compom parties. Why is it making sense? Because Google doesn't know which loser is actually searching for compom party, right? If I'm searching and if I'm logged in, if they really figured out my narcissism, they should just fill it, fill first 100 pages with just me, okay? But if I'm not logged in, they should hedge their bets. To some extent, this user has uncertain preferences, because I don't know which human this human is, and so depending on their entity, their actual identity, they might have a different preference. And so, since you don't quite know what to optimize for, you hedge your bets by saying, I'm going to generate a diverse set of results. So something that people don't tell you if you think in terms of search engines is, if you give a query, right, and then you have results R1, R2, etc., Rk that you're trying to show, people will say the important thing is to make sure that each of these results are very similar to the query. So it's as if you're trying to put the results in the order of their similarity to the query. But that's just one of the requirements. The second requirement is that they are as dissimilar to each other as possible. That's the diversity. Because otherwise you can just have multiple copies of the same page under different names be presented in the top 10 results, and that will be completely useless. Okay, again my point is that this is done. AI is not the only place where we are trying to have programs and humans together in the loop. And the other people who actually don't have this sort of a grandiose view that we will eventually possibly eliminate humans, and they can just be sitting on the couches and the robots will take care of everything. They don't have that kind of a grandiose view, and they always assume that humans in the loop need to be made happy. And AI people didn't necessarily do it for a while, but now increasingly there's a lot more interesting work that's going on, which actually takes it's just not a nuisance anymore. There are interesting research problems that come in because there is humans in the loop. Okay, these are some of the things that caught my attention in terms of trends. There's more of the work that's being done in AI that's sort of human aware than before. Okay, then basically, in fact, in the old days, AI agents were happiest when they are on Mars, where there are no other humans, unless you believe in conspiracy theories. Okay, and they didn't like it when they have to deal with humans. I mean, even in the Grand Challenge, DARPA Grand Challenge, remember where we put the first challenge? Nevada desert, right? Where there are no other humans other than other DARPA Grand Challenge cars. And then the second one is actually bring them to LA, and that's much harder, basically, when you have people. We have to deal with it ourselves, because the most important piece of knowledge that you wish you had when you are driving is what the heck is going on in the head of the guy behind you and the guy in front of you. Because your safety is very much dependent on what's going on in their heads. Right? If suddenly they feel like, I think every once in a while you'll say, if somebody would get onto the wrong lane and go opposite to the traffic and then hit somebody. And how much can you plan for this? So the point is that we were much more happier with like an antagonistic stance like chess, where let's crush the humans, or a sociopathic sense like be on Mars, and it'll take 8 minutes. When you say I'm falling, it'll take 8 minutes for that to come down, maybe less than 8 minutes, maybe 4 minutes to come down, and another 4 minutes to say don't fall, from the humans. So it's like the teenagers dream, let's go as far away from parents as possible, and robots always wanted to go far away. But now it's much more interesting to have what are the issues that come in, Okay, so that's some things that we could talk about, that I thought of mentioning. You could think of other things, maybe. Any other questions on this? Okay, so if not, then we'll do planning, and I'm basically just going to go quickly through that chapter. Since this is also the first technical topic, maybe I'll say certain things that are also be relevant to other topics that we will consider later on. So the big picture, of course, is synthesizing goal-directed behavior. You are selecting actions, and you are making sure that if you do those actions in some order, you go from the initial specification to satisfying some goals. Okay. The simplest scenario we'll start with is goals somehow have to be true by the end of the plan. Nobody is telling you that they should be true in the middle, or that you should go through certain sequence of states, all of which are reasonable goals, really speaking. Right? We do actually think in terms of goals that are, in fact, the entire trajectory of your behavior should be safe. A goal of safe driving, for example, is reach your home, but don't drive on the shoulder for extended stretches of time, for example. Okay, not driving on the shoulder for extended stretches of time, it's not a goal of attainment. It's a goal that is satisfied during your execution. So those are sort of trajectory goals, for example. So we'll get to them later, but for now we'll assume all that matters is where you get to. It's the end point, and certain things have to be true in the end. That's the one that you read in the planning chapter. Okay, we will see that in the simplest case, actually, actions are, the plans that we are interested in are essentially sequences of actions. But in the most general case, really, they are mappings from states to actions, or from sensory inputs to actions. If you can tell what the state you are in is, then you can say, if you are in this state, do this action. That would be called a policy in general. In a deterministic world, you just have an action sequence, so you can almost close your eyes, because you know the initial state. You can close your eyes and do actions one after other, and you will still be able to reach the goal if in fact the goals were supposed to be reachable by simulation. Okay, but if there is uncertainty either in the initial state, or incompletely specified initial state, or stochastic effects for the actions, and all these things are happening, then you essentially have to look at the state that you are in and decide which action is to be done. Now, on top of it, if you don't have good sensory, good perception, that means you actually won't know which state you are in. And so all you know is you get some percepts, and those percepts might come from multiple states which are equivalent with respect to those percepts, and you still have to decide what action to do. Yes. Okay. We will get to policies obviously later. In fact, the two other things that I talked about, one is handled essentially in fully observable Markov-Radiation processes, and the second is handled in the partially observable Markov-Radiation processes. Okay. Okay, so the other thing in looking at the planning, I'm not sure whether you got that out of the reading of the chapter or not, but we tend to, I'm slowly understanding why there's a fan here, because I'm sort of heating up here, but we tend to look at domain-independent planning. We keep talking about something called domain-independent planning. The idea there really, paradoxically enough, if you are talking about, so suppose you have domain, okay, domain-independent planner and a domain-dependent planner. Okay, they take some input and give the solution for the problem. The question is, which one takes more inputs? What do you think? I mean, does the domain-independent planner take more inputs, or domain-dependent planner take more inputs?
Domain-independent
planner takes more inputs. Why?
He does not know anything about
exactly. So, in some sense, I mean, if it's obviously it's not paradoxical for you, but it may be for some other people. A domain-independent planner, in some sense, all it is a good search engine. It requires the domain dynamics to be provided as part of the file, plus a problem. Okay, so this is domain-independent, this is domain-dependent, and then you can say D-dependent star, which is one goal for that domain. Okay, so for example, have you ever gotten onto these trains in Atlanta airport or any other airport, which seem to be pretty intelligent, right? They seem to stop, you get on, they seem to go. Okay, they don't ask you where do you want to go. They don't ask you whether you want to fly there or go. So first of all, they are in the going business, train going business, they are domain dependent, but their goal, the only goal they have is, if you get in, I'll close the doors and take you to the baggage handling. So the goal is also inbuilt. Okay, so the least number of inputs are taken for this. This guy just, you switch it on, it will do something, whatever it is it's built to do. Okay, and this guy will be switched on, it loads, it already has a domain built in, it just asks, so what goal in that domain do you want to satisfy? This guy, you switch it on and says, okay, where's the domain? Where's the initial state? Where's the goal state? Okay, so, and so in some sense, essentially we will be looking at this problem, but if you happen to know that your entire life depends on a very specific domain and a very specific standard initial state, eventually you might want to just compile down whatever you know into a more efficient domain-dependent planner. And then further, if in fact your goal also doesn't change, you will eventually compile it down to this. Now the usual difference that people make is, if you look at a problem and you start writing a C program which just solves that problem, then you are going from this direction. Whereas in planning we are going this direction. Okay, domain independent means you're going this direction. Okay. Okay, so unless I tell you otherwise, we will be talking about domain independent planning. Okay, that's the normal expectation. So we are going with assuming that the domain will be specified, the initial state will be specified, the goals will be specified. Those three things have to be specified. Okay. Okay, so this is my favorite diagram. This is the usual intelligent agent diagram. Everybody has some version of it if they're doing AI. And obviously you have an agent which is in some environment, and it's affecting the environment through its effectors. It's perceiving the environment through its sensors, and the big question is, what do I do next? Okay, now what do I do next depends on what goals it has, of course. And the goals themselves can be, as I said, goal of being in some place finally, or much more complex reward metrics, such as try to do the right thing. In fact, there was, I think the Spike Lee movie, Do the Right Thing. That's the main advice that we give to people, right? So just do the right thing, and because you will have different goals, but just do the right thing. Okay, that would be a harder kind of a goal. It's more of a complex reward matrix. That's for that. For the actions, once you know what your goals are, the actions that you can do, you could have obviously bad effectors, in which case you are stochastic effectors. You can be non-deterministic effectors, or you can be deterministic effectors. Deterministic means you know after that action is done in a state, you know exactly what the next state will be. If you happen to know what your current state is, and you do this action, you know what the next state is. Okay, this is important to understand, even though it doesn't look like a big deal. All a deterministic action says is, if I give you S1 and I do A, I'll know what is the next state that will happen after A. But if I happen, how do I know what my state is? That depends on my perception. If I have bad eyesight or bad hearing, then I might think I'm in one of these 100 different initial states. Okay, so then essentially what you currently have is S1, S2, etc. to Sn. Is any of these states, is one of the states, is the real state you are in. And then if you do a deterministic action from this, you will again get a set of states. The only difference is that when you apply the action to these states, each state gives at most one extra state. One new state, not more than one. Right? So the outcome being, in fact, when you have sets of states, we will use this terminology called belief state. Okay, and one of the interesting questions is, although we will be first discussing deterministic actions where you apply an action to a single state and you get a single state back, once you start having uncertainty and incompleteness, you have to start thinking in terms of belief states. And in the case of belief states, you apply an action to a set of states to get a set of states. Or you can also apply an action to a single state and get a set of states. If that happens, then your action is non-deterministic. Because the only way you can take certainty and blow it up is you have an action which introduces the uncertainty. Okay? And then of course, furthermore, there is this other distinction we'll talk about, which is if I give you a belief state like this, that is non-deterministic, because I didn't tell you what is the likelihood that you will be in S1 versus S2 versus Sn. If I also give you a distribution over these, and say this is the distribution that you will likely be in this state versus this state versus this state, then that would be stochastic dynamics. Okay, and what happens in those cases is when you apply an action to a belief state with a distribution, you'll get a new distribution. That's all. Okay, now one can actually argue that it doesn't really matter if in fact the world has S1 to S million states, okay, then the distribution is always over those million states. If you have less uncertainty, that means many of those states the probability is 0. Okay, and if you happen to know exactly where you are, then you have this impulse kind of a distribution where in one place all the probability mass is concentrated. Of course, we are talking about discrete, so it's not even impulse, it's just in one place you have 1.0 probability. And then when you do the action, then if it is an uncertain action, it sort of spreads the distribution. Okay, and in general, if you start thinking in terms of distributions, then what the sensing does is to. So if you think in terms of, suppose I have S1 to S10 power 6, and then I have a distribution like this versus like this, then this in some sense is more certain than this. Okay, and then you can also have distributions like this. That means they're bimodal. That means you're quite likely to be present somewhere in this region or somewhere in this region. And actions will just change distribution to other distributions. Okay, but again, we are jumping ahead of the situation. For originally, we'll only look at deterministic actions. Okay, but if the actions are not deterministic, if they are stochastic, then all sorts of interesting things will start happening in terms of we are having to deal with distributions. The other thing that matters about the actions is whether they are durative or whether they are instantaneous. The important thing about durative is that as the action is taking place, the world can still be changing. Okay, and as to whether world is, and in fact, so I said as the action is taking place, world can be changing. In fact, that is not the only reason durative actions are important. Another reason durative actions are important is two actions may actually have to overlap to do something right. Okay, for instantaneous actions, eventually there is no point in talking about simultaneity of instantaneous actions. Whereas durative actions, obviously you can talk about simultaneity. So the classic case is, you're trying to lift this table with your friend. So you lift and then you stop, and your friend lifts and on that side and stops. You're not going to go anywhere. So you have to have some, simultaneity of the action. Okay, so the reason this is interesting is little later when we start talking, and you may have read in the planning chapter that sometimes you can start talking about partially ordered plans. Now, in the case of actions which are instantaneous, partial ordering is just a search convenience. It has really no execution semantics. Okay, a partially ordered action will be sequentialized this way or this way. It's just like database. And sometimes in transactions, processing in databases, you might consider allowing certain transactions to be parallel. What that only means is you don't know which order they will get serialized. And so it better be right. Better your money from ATM won't disappear irrespective of which order they get serialized. That's all you need to make sure. Okay. Whereas on the other hand, when I have durative actions, I have to sometimes make sure that these two actions happen at the same time, because otherwise certain effects won't actually happen. That's the additional thing that you do. Okay. Then the first thing that I mentioned, which is that maybe the world is changing, that sort of relates to whether there are other agents in the world or whether you are the only agent in the world. So that's basically static versus dynamic. Okay, and in fact, between static and dynamic is multi-agent. That means, dynamic essentially means the world is changing, I don't really know why it is changing. Multi-agent means I know some of the reasons why it might be changing, and I can try to, plan for it by sort of modeling my opponents, modeling my either opponents or my co-workers, and coordinating with them or, playing against them. Okay. So those are all the things that make things harder. Obviously, all this, whatever this color is, the yellow colors are bad, and the brown colors, it's not brown really, is good, because from a computational point of view. Okay, from the planning, from the actual interestingness of the problem perspective. So if I only have this brown one, so static, deterministic, fully observable, instantaneous actions, and then the other thing is propositional. What I meant by that is the world is essentially discrete. That means the knowledge about the world can be represented in terms of a set of discrete state variables, no continuous variables. Okay, if that is the world, that's the world you're looking at, then that corresponds to the simplest kind of deterministic planning that's been called classical planning. Okay. Now, then we will basically understand this, and part of the expectation is also that when you understand this and when you do this fast, then hopefully you can do a reasonable job of doing the harder ones also fast. Okay. In particular, we'll see that apart from just understanding how to search for plans in the classical planning scenarios, we'll spend a bunch of time talking about how to improve the search. What's the effective heuristics for improving the search in classical planning scenarios. And part of the reasons for that is, as I'll say in a minute, in some sense, classical planning problems sometimes might actually occur for you, but more often than not, it would be the substrate into which you might be able to compile other problems. Okay, and furthermore, of course, so that there are two different ways this can be useful. In fact, and both have been done. In trying to understand how to solve classical planning problem, you might get ideas as to how to solve other problems. So the transfer is occurring through your head. Okay, the more interesting transfer, which is more obvious transfer that also has been occurring, is people just find a way to compile down, let's say, a stochastic planning problem into a classical planning problem. A planning problem under partially known initial states into a set of classical planning problems, for example. And so then this becomes your own compiler, compilation substrate. Okay, so and then the other ones, start coming up as you start removing each of these assumptions. And the way the work has occurred in this field is you remove assumptions. You make all assumptions at the same time, and you remove them one by one, and then after that pairs, after that 3 at a time, and so you will be busy writing lots of papers. Part of the reason also is because it's in fact hard to remove any of these assumptions and do anything, computationally feasible. Okay, so if you remove the instantaneous assumptions, you'll get durative actions, and you talk about temporal planning. We might talk a little about that. If you remove propositional, you'll get numerical constraints and numerical variables, and you'll start having continuous planning with discrete planning together. That's interesting. There is some work which kind of combines integer programming, linear programming techniques with the search techniques that we'll talk about here. That's one way you can solve those kinds of problems. You remove static, you get dynamic, and you can deal with dynamic by replanning, for example. Okay, so the idea is, if you are in, let's say, what's called an ergodic domain, that means where every state can be eventually reached from every other state. Okay, and that's a great name for a simple idea. The advantage of ergodic domain is there is no death. Right? The interesting thing about death, unless you are a firm believer in afterlife and ways of coming back to North Carolina or something, essentially, death basically means from the state of being dead, you can't reach any other state. Right? Okay, and so there are no irreversible failures. If you have ergodic, means essentially whatever happens, you can always get up, dust off your shirt and start walking again. And in those cases, one way of dealing with dynamism in the environment, or in fact pretty much any model reduction in the environment, any problems in actually full modeling of the environment can be handled by just coming up with a plan, start executing it. When you find that your plan isn't going anywhere, replan. The only time that will actually not work is, in fact, the domain is not ergodic, in which case you will basically die, and then so there is not much of a replanning left after that. Okay, so you could do replanning, or if you have a multi-agent scenario, you actually plan for coordinating with the other agents, or you actually plan to anticipate what the other agents would do, and still try to improve your the min-max sort of game tree search kind of things, where you would try to reach your goal despite the fact that there are these people who are trying to make moves to stop you from getting anywhere. Okay. So and then there is partial observability. If you remove the observability of the world, then you can start having an incompletely known initial state, for example. And if you have incomplete known initial state, then you have belief states, and then you can be applying. Suppose you have partially observable world but deterministic actions. Then that means initially you think you are in a set of possible worlds, but then that set can never increase in size as you do actions. It can reduce in size, but it will never increase in size. And when the reduction occurs, then in some sense you increase the certainty of your position. A classic case that I keep talking about and many of you will understand is when you wake up in the middle of the night in a strange place, and then you need to go to, let's say, bathroom, you don't quite know where you are, and so you don't quite know what actions you should do to get into the bathroom. And obviously maybe other people may be sleeping, you don't want to put on the light. Okay, so since you don't know where you are in the room, the thing that you try to do is first try to hit a wall, and then follow the wall. Okay, now hitting the wall may not be the shortest path to the bathroom. Right? I mean, you are here, the bathroom is here, but you don't know that. So you go hit the wall here and then follow the wall until you find a door and you get to the door. Right? And that's basically what you're doing there is you're first reducing the uncertainty of your position, you're localizing yourself, and then you are making progress towards the goal once you localized. And that's the kind of thing that happens when you just have partial observability but still more or less deterministic actions. If you have both, then it will be harder. So then you can have stochastic actions and everything else remains the same, but the actions are stochastic. There, you know which initial state you are in, you do the action, and you know that you will be possibly in one of these 1500 different states. But then after doing the action, you can actually look around to see which state you actually reached, because everything else is still there, observability is there. So after doing the action, so for example, before I toss the coin, you don't know whether it's going to come heads or tails. Okay? And after I toss the coin, you do know what came. I mean, as long as it's observable world, so you know, okay, it came heads or it came tails. So then essentially, the model for that, for example, the stochastic planning essentially will be that model, and in fact, we'll look at MDPs become like a good place to start from, but there are ways in which you can extend classical planning for that. Okay, and what else? So then you can also play this game by doing two things at a time. Durative and continuous can be removed at the same time. So that means instantaneous and propositional can be removed at the same time. You'll get something called metric temporal planning. You can remove deterministic and observability at the same time. You get POM-DP. Okay. You can remove deterministic, observability, and dynamic. Deterministic, observability, and static at the same time. That means you have other people in the world, and you don't know what's going on in their heads. And you have shaky hands, okay, and that's close to what we live in right now, right? And then the simplest model, notice that the simplest model in atomic case for the classical planning is really finding paths in a graph. It's just that it becomes more interesting because we do it at a propositional level, but otherwise it's just finding paths in a graph. Okay, atomic model is finding paths in a graph. For MDPs and POM-DPs, the atomic models themselves are interesting. In fact, they're quite different from just finding a simple path in a graph. Okay, it's like MDPs and POM-DPs find policies. Okay, and the model for all three going away at the same time is DEC POM-DPs, decentralized, partially observable Markov-Addition processes. And anytime you do one more observation goes out the window, then one more assumption goes out the window, then the computational interactability just keeps going up. Okay, so to give you an idea, for example, classical planning in the simplest case we'll see is p-space complete. And a way of figuring this out, of course, is that the simplest way to remember this is since you already looked at strips representation, which I'll be repeating in a minute. Within that representation, you can write a Tower of Hanoi problem as a problem. The moment I say this, then you know that given the input, the solution for Tower of Hanoi problem would be exponentially long in the size of the input. Right? And so just finding whether or not something is a solution is no longer polynomial. Because you have to simulate each of these exponential number of actions just to even see whether you have reached the goal state. Okay? And so it's no longer in NP anymore. And what can be shown is this is p-space complete. It's the hardest class of problems that can be done with polynomial space. Okay, and if you start removing, for example, if you start removing the observability or the deterministic, then you start going from there to x prime and double x prime. And if you're into the complexities, I'll show you papers, although I won't probably discuss that much about them. But there are people who actually first show that these complexities do in fact increase. Okay, so it's not surprising, and many other places where you will start saying it's still decidable. So the most ambitious, most optimistic thing you can say is under these conditions the problem is decidable, which is like the last thing computer scientists do before they die, right? Because if it's not even decidable, what do we do? So in general, these problems can become hard, as you keep removing these assumptions. Okay, yeah, fun. And you can also remove, for example, stochastic and durative, and you essentially the models you get is semi-Markov-Addition processes. So MDPs themselves give a variety of atomic models. You can think of path finding as a degenerate MDP, and then finding policies is MDP at the atomic level. Finding policies in partially observable worlds as POM-DP. Finding policies in partially observable decentralized world as DEC POM-DP. Are finding policies in fully observable but durative actions as semi-MDP. And these are all, interestingly, they're all atomic level. So the thing that I want you to remember is, this one. So all the MDP stuff is at the atomic level. Min-max stuff is also atomic level. Min-max is a sort of adversarial reasoning with the other agents thrown in. Okay? And then trying to figure out how to do them more efficiently at the propositional and relational levels, that's a very important aspect of doing things faster. Okay. Any questions on this one? Okay. So let's do modeling of deterministic planning problems, action states, and correctness. You looked at some of these, so I'll go just fast. Stop me if you are getting lost or something. So the simplest assumption, as I said, is we'll first look at the atomic model. Atomic model is just a graph. You have states, and the transitions between the states are represented by directed arcs from the one state to another state. Okay, and to find whether or not you might be told that you are Z. So if you think about that kind of a scenario, essentially you have so you might say here is S1, S2, S3, S4, S5. There is a way of coming here, there is a way of coming here, there is a way of coming here, and there is a way of coming here, this is a way of coming here. That's your transition graph. Okay? And I might tell you that, since it's a deterministic, it's a classical planning problem we are looking at, I might tell you that I'm interested, I'm in S1. So I told you which state I am in. Because in classical planning you know completely where you are. So you're just told one specific state that you are in to the plan. Okay? And now what about goals? The interesting thing is goals don't have to be that you must be in a very specific state. You can identify goal states without making, in fact the problem becomes easier by saying, well look, either this or this are goal states, for example. I can say that. Okay, and there is an essential asymmetry in the goals and the initial state. If you have uncertainty as to where you are, your life is harder. If you have uncertainty as to which goals you need to achieve, that's actually not a bad thing, that's a choice. That's like either do this problem or do this problem. You can pick one of them. Of course, people actually say, don't give us choice, we don't know how to deal with the choice, but it's like really, truly it is a choice. You can either go to S1 or go to S5. So it's no worse than being just given one of them. It's actually cheaper, in any computational sense. Okay, so the goal is less demanding if in fact the goal condition is holding in many states rather than a single state. Right? Whereas the problem is harder if your initial state corresponds to multiple real states, because that means you don't quite know where you are. Okay? That's what happens across the board. In fact, that's why the very first thing, you guys read about regression, right? So progression, it starts from a single state and just keeps going forward. You start from a single state, you do a deterministic action, you get a single state. You do one more deterministic action, you'll get another single state. At some point of time, you'll check whether the single state you have on your hand is a member of any of these lucky chosen states. If it is, you stop. That's how progression goes. Regression, on the other hand, think about what happens if you're doing regression in this graph. So in some sense, what I told you is, if I want to actually go from S1 to a goal state, now I just need to find a path from either S1 to S3 or S1 to S5. Okay, anytime I find one of these nodes, then I stop. And then I'll output the path. Right? Okay? Whereas if I'm doing regression, then the interesting question is I have to start from S3 and S5 in some sense simultaneously. That causes some headaches. This is the problem that people face when they have choice. Right? Basically because they essentially, so should I start trying to prove this theorem or this theorem? If I'm the guy with the kind of luck I tend to have, I'll pick the theorem that cannot be proved. And 3 hours will be over and the exam is over and you haven't proved anything. So then you'll say, I wish you gave me no choice at all. So in fact, there was this one particular qualifier that, in my grad school, they used to have qualifiers to get into, in the PhD program. And I remember in one qualifier, there were 6 questions and only 5 need to be done. And somewhere in the, thankfully I wasn't one of the people taking that exam. Somebody told me this happened. Somewhere at around 3/4 of the exam was over. After 3/4 of the exam was over, the professor, in fact, Lavin Kanal, showed up and said, "Oh, by the way, don't work on problem number 5. It cannot be solved." right? And God help you if you wasted all your time trying to solve problem number 5. You know, Lavin can actually say, look, I had the choice, so really I didn't, you know, mess with you. But on the other hand, if you're regressing by picking the wrong goal and keep trying to make that happen, then you have lost 3/4 of the time, essentially. Okay? So when you're doing regression, actually, it's in some sense it could be an easier problem, but it could also be search-wise inefficient. Okay? One thing that we will notice later on is progression. Actually, as I said, it always happens in the space of completely specified states. Every search node is a completely specified state. Regression happens in the space of sets of states. Okay, so in some sense, regression space can be much larger than the progression space. Because if there are n states, then there are 2 power n sets of states. And another thing is that there may be sets of states which are empty sets. And if you have propositional representation, I can nicely give you a nice little propositional formula which is nice and complex. It just entails false. That means it's an empty set. And now you might say, no, why can't you just figure that out? But unfortunately, finding that a formula is empty is a hard problem too. Okay, so those are the, so again, this is this issue of choice kind of catching you. Even though, you know, having multiple goal states is sort of better, you could, by being bad in deliberation, you know, spend all your time trying to figure out. In fact, one of the most famous donkeys in probability and computer science is a donkey by name Buridan. A Buridan's donkey. So Buridan basically talked about this proverbial donkey which was placed equidistant from 2 bales of hay, and it could not figure out which one to eat from, and so starved to death. Did you understand what I'm saying? So this is sort of paradox of choice. And so in fact the very first probabilistic planner that got a lot of citations was called Buridan. And you know, and it also didn't do much faster than the donkey did. But the point, of course, is here the problem is not hard, but you can make your life harder by just thrashing between which one do I do, unless you're careful. Right? I mean, whether a problem is hard and easy versus whether you know how to solve it are completely different issues. Right? I mean, as we speak, I always feel that somebody in the industry is coming up with yet another exponential algorithm for topological sort. You know, it's because it doesn't call itself topological sort, it just happens to be a subroutine in something they're doing, and they'll just write some dumb algorithm and that will be an exponential algorithm. Right? And of course you might say, no, don't you know, I mean, haven't you read JSCM 1952 itself, it's been shown that it's a polynomial type. And they have no clue. Okay, so the fact that it's an easy problem doesn't mean you will write an easy solution for it. Okay, you can do exponential time algorithms for normal sorting. Right? So there is that interesting issue about regression that you want to keep in mind. One of the other things is in the atomic world, in the space of explicit states, even writing regression planner becomes a headache. Because in some sense you need to now start talking about graph search where you have multiple sources and a single destination. Okay, it's much easier. There are many more algorithms which start with single source, multiple destinations rather than the vice versa. Okay, so in fact, people who look at, and in fact there's something I'll mention later too, but the MDP literature, because even at the atomic level, stochastic planning is hard. For the longest time, most of the work in stochastic planning was done in atomic level, basically at the MDP's level. And then there is a paper that you might wind up reading, it's like this 90-page behemoth on decision theoretic planning, review of this, overview of decision theoretic planning. And there's a whole section there where this guy essentially is kind of going to paroxysms describing regression, saying those guys in classical planning have this fantastic technique called regression. And I never thought regression was such a fantastic technique. Because I was just, I was using it and didn't particularly think it was a fantastic technique. You will understand why it's a fantastic technique from the point of view of somebody who's trying to do regression from an atomic level. Because then essentially you're doing multi-source, single destination problem. Whereas A regression in a propositional level is in both sides. It's a logical formula manipulation. Okay, fine. So one other interesting thing, of course, is these are all just transitions. As far as planning is concerned, we have this notion called action. So normal path planning will essentially, suppose it were to find this path, right? It will just say S1 to S3, S3 to S4, S4 to S5. But normally you tend to think of plans as sequence of actions that you are supposed to do. So you need to actually assume that these transitions have names. These transitions have labels. And in particular, actually, so this might be A1, and this may be A2, and this may be again A1. And I can also actually say this is A1 too. What that means is there is an action called A1, which when it is done in S1 gets you to S3, when it is done in S2 gets you to S4, when it is done in S4 gets you to S5. So really an action is an S by S matrix. Here are all the states, here are all the states. Each action basically is zeros and ones in that table. Okay? And that's what an action is in the atomic representation. And of course, the full transition model is adding up all these matrices, because they're all going to be the same sized. Okay, and you add them all up, then you have all the transitions in the same place. Agreed? So that's basically the transition model. Okay, that's the atomic transition model. And these are called explicit state space models. And within this kind of a space, it's still interesting to talk about optimal paths. That's what your A-star search tells you, for example. Okay, so A-star search takes the place of MDP in the context of explicit state space models with deterministic actions and completely non-linear states. Okay, so now what's wrong with this? Obviously, transition systems are great. In fact, the first thing you try to understand every problem at, is at the atomic level. If you don't understand it at the atomic level, don't expect to do miracles of trying to do it at the propositional and the relational level. Because the semantics for the correctness of propositional relational levels would ultimately be in terms of the atomic level. Okay, so they, in any random problem, even if the problem becomes harder, if you start removing some assumptions, you may be able to use atomic semantics too. Okay, so that way transition systems view is very useful. But the problem, of course, is that all actions are just the same size. And in any reasonable world of, let's say, 10 state variables, 10 Boolean state variables, I have 1024 states. And so each action is a 1024 by 1024 matrix. Agreed? It's a 1024 by 1024 matrix. So actions are like very huge, And now the advantage, of course, is this allows the action to be arbitrarily complex. It can do different things in different states. Okay, it's the most general representation you can have for actions. But it's also making the representation very large. And furthermore, there is no structure. It's hard to see the structure of the action. It's just basically, a bunch of directed arcs in the explicit states. Okay, so that's your problem with transition systems. So we look at state variable models. So it's useful to know what you would be doing earlier, and then you talk about this, and if you ever have to prove the correctness of this, you go back to that model. That's the normal way you prove the correctness. Okay, and that's true for whether you go to MDPs, PAMDPs, etc. If anybody comes up with, there are people who came up with propositional models to stochastic problems. And then they show the correctness by actually showing that the equivalent atomic MDP does actually reach optimal policy. That's the usual way you prove. Okay. Okay. So now in the state variable model, we are assuming the world is made up of states which are defined in the terms of state variables. I assume in the beginning they are Boolean. Within the planning community, there's like a big deal. For the longest time, most planners, just by convention, used Boolean variables. And nowadays, most of them use multi-valued state variable representations. Okay, so they do that even if the specification of the domain is in Boolean propositions. So they quickly run some preprocessor which essentially unearths the fact that you took a multi-valued variable and made it into a bunch of Boolean variables and realizes that this is a single multi-valued variable. And then uses that representation. I say this because I think, in fact, the chapter you read may have mentioned SAS representation. Did they mention SAS representation? If not, you will be reading, the first paper you will read would be about landmark heuristics, which are some of the most recent effective heuristics. You talked about planning graph heuristics in the paper, in the chapter, but we will also read a IIII 2008 paper on landmark heuristics, which we'll probably get to by the next Wednesday. And then that one just assumes that, SAS representation. It's not a big deal. It's just basically using multi-valued stuff, Boolean statement. Okay. So first now, in fact, in the discussion that I'm doing, I'll start off, many of the things I'll say would be actually directly relevant to multi-valued state variables. Okay. And there are very few that are actually thinking only in terms of propositional variables. But the advantage of Boolean is we can just think of them as propositional formulas. Okay. Any goal will be a propositional formula. Okay, so states are complete assignments over state variables. You're thinking of discrete state variables. So if there are k Boolean state variables, then there are 2 power k states. Okay, actions change the values of the state variables, and so the idea is they doctor the state variables. So you start with a set of state variables and their values, and then when you apply the action, then it just changes some of those state variables values. Now in the Boolean case, state variables are true or false, and when you do the action, then it may change some of the existing variables to true and some to false. And remember that you will never apply an action unless the state is completely specified, because it's classical planning. You know where you are. And so every time an action will be applied to a completely specified state, okay, and then it will just give you a new state. The only thing that it will make sure, now notice that in this case, A1 can be done from here, it can be done from here, it can be done from here, but I didn't say whether it can be done from here and, I didn't say, for example, what happens if I do it from S3. In some sense, you can't do A1 from S3. That's what it means. Right? Okay? So basically for that to make sense, you need to allow for the action representation to say, unless the state has certain properties, I won't even be applicable. And then when it has those properties, then I will doctor the state this way. That's why you wind up needing preconditions. If an action is applicable everywhere, it doesn't need preconditions. Okay? The moment an action is applicable, in fact, preconditions are sort of a discontinuous thing. They make actions discontinuous because certain states, in fact, from a semantic point of view, if you apply an action in a state where the preconditions are not satisfied, logically the world ends. Because you try to do something, but now of course one precondition of lifting this table is that you are a reasonably well-endowed human being, and I tried doing this and it doesn't seem to lift, but the world didn't end. Okay, just the world stayed where it was. Most of the time when an action fails, it'll just be a self loop. Okay, if I basically were to say, if I allow self loops, and then basically if I do S3, if I do A in S3, I'll still stay in S3. Essentially. In that case, I no longer have preconditions for actions. I only have effects. And then state, and then in that case also, the action will be sort of a total function. That means for every state, its effects, a new state is defined. Okay, so the preconditions actually make things mathematically clumsy, in terms of proofs and so on. But also they make life simpler in some cases, because if the one way of stopping something from happening is make sure that one of the preconditions will not be holding, then that action cannot be applied. Okay? So here is a description of Block's world. Basically I wrote in terms of the state variables I'm using is untable x, on xy, clear x, handle empty, holding x. Now notice I have provided nice relational structure, right? It looks as if the untable is a predicate with one argument, on xy is a predicate with two arguments, etc. But whether or not the structure of the representation is used is not, I mean, basically, in fact, most of the propositional planners essentially think of this on table A as on table dash A. So it's a proposition. Okay. In fact, most of the, and this is in fact the difference between lifted planners and propositional planners. Most of the ones we'll talk about in the beginning would be propositional planners. So I'll assume, even though I write these things with nice syntax, with predicates, with action and effect, arguments and so on, when you apply that, the engine itself thinks of an action with propositions as preconditions and propositions as effects. Okay. So here are some, here is a initial state, on table A, on table B, clear A, clear B, hand empty, and my goal state is not clear B and hand empty. And the peak, these are some of the actions, I gave some names, precondition, hand empty, clear X, on table X, and these are sort of schemas. And so if I pick up A, then I will put instead of X, I'll put A. But it will still be a propositionalized action. So in some sense, most planners, what they do is when they start doing, most modern planners, when they start doing the problem, they first do a grounding phase. Believe it or not, some planners die before they start. Why? If you have way too many relevant objects in the problem, then you are just happily just grounding everything without making even an epsilon progress towards the goal. That's actually expected to be one of the advantages of doing relational and quantified representations, because you'd only concentrate, if you do full grounding up front, in some sense you're compiling your relational theory into a propositional theory first, and then doing reasoning there. A much smarter idea would be to only look